Quick recap for last class. Last class we discussed about that thermometers are devices which are used to measure temperature. Temperature is a measure of the total amount of energy stored, extractable energy stored within an object by means of its motion, by means of its particles motion. The motion can be of two types. It can be vibration, it can be translation. We talked about how solid, liquid, gases, particle can have these kind of motions. We talked about that temperature measurement is an indirect process. We cannot directly measure the temperature, and the properties of multiple different substances which changes uniformly with the change of temperature, those properties are called thermometric properties, and measuring the change of those properties we can easily measure the temperature. And what we have also seen that we have also talked about the temperature scale, the two type of temperature scale which are most widely used for our purposes: degree Celsius scale and also the Kelvin scale. Kelvin scale happens to be the SI unit. Sorry, the base base unit of temperature. Temperature is a base quantity, and the key formula that we talked about last class is that for any change of thermometric property, this equation will hold true. Delta theta is directly proportional to delta x. That x can be the change of the thermometric property. So if it is some volume in liquid, it will be directly proportional to the change of volume. If it is, we can also convert that volume into length by means of using a uniform cross-sectional area within the thermometer stem or thermometer body. So in that case, the actual formula that governs liquid in glass thermometer is delta theta divided by proportional to delta V. We can write this as delta theta proportional to the fixed cross-sectional area into change of height. Because A is also a constant, we can input this within the proportionality constant, so it can simply be removed. So delta theta proportional to delta L. Achha, I should write L over here. No. Erase. Why can't I erase? Okay. Delta L. So this is the governing equation, and from this governing proportionality for liquid in glass thermometers, and we can use this proportionality to make an equation which look like this: the unknown temperature minus the one of the known lower temperature, let's say theta low, divided by theta high minus theta low, is equal to the value of the thermometric property. In this case, which should be L, because we're talking about the length of the liquid column. I'm using the term liquid because liquid in glass thermometers can be made from mercury. In some cases, they're also made from alcohol. To be honest, we can use any liquid that expands uniformly with the temperature change, but mercury and alcohol happens to be the most common popular choices for multiple reasons. And theta, so here we can write the length for the theta temperature. So this is the length that we'll be measuring from the thermometer minus the length for the low temperature divided by length of the high temperature minus length of the low temperature. So if we use this equation, we can calculate this unknown temperature by measuring these three lengths, and these three lengths for relevant for these three temperatures, and we can calculate the theta unknown pretty easily. The beauty of this equation is that this equation is applicable for any range of value that is given, as long as it is not exclusively dependent upon the temperature scale that is. So this low temperature and high temperature doesn't essentially have to be 0 and 100 degrees Celsius. But if these two temperatures are 0 and 100 degrees Celsius, in that case, the formula can be rewritten as 0 divided by 100, because it would be 0 minus 0, theta minus 0, sorry, theta divided by 100, because it would be on the numerator side, we're going to get theta minus 0. On the denominator, we're going to get 100 minus 0. So they basically become theta minus 0 equals to L theta minus L0 divided by L100 minus L0. So that can be also another equation. This is basically the equation that is available in your course, in your book. I personally don't like this very much because this limits our opportunities to measure the temperature for multiple different variables. I like this one better. So this is the part up to which we actually discussed last class, and we also saw the solution for 2 MCQs and discussed the application of this formula for multiple different cases. In today's class, we're going to talk about that how does a thermometer work and what are the specific properties which control some of the useful characteristics of a thermometer. So I'm going to use two different, okay, let me just have a look at the syllabus. Let me show you as well so that you can understand what I'm talking about. This is 22. 2022 syllabus. 2022 syllabus. Let's just jump into thermometer. Energy, temperature. Explain how the physical property which varies with temperature may be used for the measurement of temperature and state the examples of such properties. Explain the need for fixed points and state what is meant by ice point and steam point. We also talked about these 2 points in the last class. We talked about the importance of pressure. Discuss sensitivity and linearity of thermometers. Okay, so they haven't essentially said what these things are, but well, I'm gonna pick up these 3 numbers: sensitivity, range, and linearity. We'll talk about these 3 properties first: sensitivity, range, and linearity. Before I directly get into this, the property of these 3 type of characteristics, let me just 3 type of properties of a thermometer. Let me just show you the basic construction of a thermometer. The thermometer can be shown to be mostly made from an uniform glass wall tube, inside of which we should have a pretty thin, long cylindrical hole, which is called the bore. So it's a pretty thin, long, uniform constructional cylindrical hole. And then at the end, this wall is going to become thinner, and this thin part of the wall is going to produce what we call the bulb part of the thermometer. So let's say this is the bulb part of the thermometer. The bulb part has a thin glass wall so that heat can very easily enter or exit depending upon what temperature we are trying to measure. This inside hollow space is filled up with mercury by a certain height. Let's say at room temperature it is filled up with this much. So I just said room temperature, so let me just label this for 25 degrees Celsius, 25 degrees Celsius. Maybe 0 is over here, maybe 100 is over here. And so this part is filled up with mercury completely. Typically for a thermometer, a couple of things that we need to appreciate. First of all, this is the part that we call bulb. This is the part that we call stem. This is the part that we call bore. Bore basically means it's a long cylindrical hole. And the bore is made in such a way that it has uniform cross-sectional area. That's pretty important. And that's basically how the thermometer works. So if heat goes in, then the mercury within the bulb will expand, and mercury within the bore will also expand. I mean, the entire mercury that is over here will expand because of the temperature increase. And because the bulb would not expand much, because it is usually made from very strong material, this mercury is going to rise up through this bore and give us some temperature value. As long as, I mean, one of the things that we have to understand, the word we have to really be careful about is what we call thermal equilibrium. This is a very important word. The word thermal equilibrium means if there are 2 objects, let's say object A and object B, if we say these 2 objects are thermal equilibrium, this essentially means the temperature of A is equal to temperature of B. That's the key meaning of the word thermal equilibrium, that the temperature of both the objects are same, which means that they are not exchanging any further heat across each other. If 2 objects are not in thermal equilibrium and they are kept in touch with each other, they will always do some sort of heat exchange. And heat will always travel from the high temperature object towards the lower temperature object, always. And it will keep on happening such that as long as there is a temperature difference, the heat energy will continue. So hot object is going to lose heat, cold object is going to gain heat. But what is really interesting about this whole thing is that the rate of heat flow happens to be directly proportional to the amount of temperature difference. This is really interesting. I'll tell you why this is interesting. Let's say if we have a metal pot that is filled up with boiling water, let's say at 100 degrees Celsius, and this is our room temperature, let's say 25 degrees Celsius, and this is theta, and this is time. Let's say in this case, time is plotted in minutes, because this is a pretty large graph. If we have a metal cooking pot filled up with boiling water, and we keep it in the atmosphere and allow it to cool down, it's going to start cooling off from the 100 degrees Celsius temperature. but it will not cool down over the time linearly. I mean, if you, let's say if you are going to measure the temperature, if you're going to play, let's say this is a cooking pot which is filled up with 100 degrees Celsius water. So it was just, this water was just boiling over the stove. You just took it off the stove and placed it onto the floor, and immediately put a thermometer right over inside this thing. Or maybe the thermometer was also within the liquid when it was boiling, but that's not very good idea, because the thermometer might actually burst under boiling water. There are a couple of reasons for this. I'm gonna just talk about those reasons after a while. But let's say we put a thermometer right in here, and what we'll see that the moment you put the thermometer over here, within a short time, this thermometer is gonna give us a reading of 100 degrees Celsius. And then as this water and the cooking pot is gonna start losing heat to the atmosphere, this temperature, represented temperature, is gonna slowly go down. So, and using a stopwatch, you can choose a stopwatch, or you can use a wall clock over here as well. For example, they are one of these wall clocks, and you can take readings after every minute, every 2 minutes, or every 5 minutes, depends. The reason we can use a big wall clock, I mean, using a stopwatch is not very essential over here, because the scale of temperature over here, time scale of temperature, or time scale of this graph is actually pretty large. A minute amount of time difference doesn't need to be measured using a stopwatch, because stopwatch is used to measure fractions of seconds. So in cases or in particular experiments where measured time has to be really precise, for example, you are dropping a ball from a certain height and you want to measure the exact amount of time it takes for that ball to reach the ground, you have to use a stopwatch. To be honest, that experiment should not be done by human beings. That experiment should be done by some optical sensors or some high-speed camera, such and such. If you are trying to measure the oscillation time period for a simple pendulum, you should use a stopwatch, because you want to measure it at a pretty precise value. But if you're trying to measure the temperature of a cooling object for a uniform time interval, you're not going to measure the time interval every second, because that's not practical. I mean, you cannot record this temperature every second. You have to go for some increase, really bigger increment, because you do understand this experiment is going to take a while. Maybe this object is going to reach to the room temperature over a duration of 1 hour. So you have to do the experiment 1 hour. So even if you take one reading per minute, you're going to have 60 readings. If you take 5 minutes per reading, you're going to have 12 readings. So you're going to have, if you're going to take one reading per 2 minutes, every 2 minutes, then you're going to have 30 readings. So that's why using a clock or a wall clock is also pretty much useful. I mean, you just look at this wall clock and look at the second hand. The moment it rotates twice around the whole circle, 2 minutes is passed, you take one reading, and then you wait for the whole thing to go around the clock 2 more time, and then take another reading. So this thing can be useful for this case, because the time scale is pretty wide, or the in between gap of the time scale is very large. So if we take the time interval, let's say of this thermometer, let's say we're going to take this time interval every 2 minutes. We're just using this example for 2 minutes, and we're going to record the temperature within a table. So this is going to be a table that looks like this: theta/degree Celsius, t/minute. So at 0 minute, we're going to get 100 degrees Celsius. At 2 minutes, we're going to get something else. At 4 minutes, we're going to get something else. 6 minutes, we're going to get something else. So we're going to make a table like this, and we're going to fill up this whole table till the temperature reaches pretty close to 25 degrees Celsius. Maybe pretty close in this case, I mean, because you can see over here, the rate of heat flow is directly proportional to delta theta. Okay, why I'm using the term pretty close, I'll entertain this in a bit. What do you need to understand? When the cooking pot is just taken off the stove and placed onto the ground, being in contact with the atmosphere, the temperature difference between the water and the atmosphere is 75 degrees Celsius. Let's say at this point it's going to undergo some cooling. Let's say within the first 2 minutes, the temperature drops to, let's say, 95. It should be more. Let's say in the first two minutes, the temperature drops to 85. So how much degrees Celsius drop do you have? Actually, I'm ভুল লিখছি এখানে টিটা হবে এই জায়গায় আর ডিগ্রি সেলসিয়াস হবে হচ্ছে এই জায়গায়. So the initial temperature was 100 degrees Celsius. Let's say after 2 minutes, the temperature was 85 degrees. So within the first 2 minute duration, let's say this is our 2 minute, the temperature dropped up to 85. So let's say this is the 85 value. Do you understand? Do you think within the next 2 minutes, the temperature will drop another 15 degrees Celsius? What do you think?
It might vary.
What would be the variation be? Is it going to be small?
Smaller difference.
The temperature is definitely going to go down. My question is, within this first 2 minutes, the drop of temperature over here, the delta theta was 15 degrees Celsius. The question that I'm asking you, within the next 2 minutes, is the drop is going to be exactly same, more or less? What do you think?
Less.
It will be definitely less, because whenever we started at the beginning of the at the starting value at t equals to 0 second or 0 minute, the temperature difference between the ambient and the hot water was 75 degrees Celsius. So, and for that starting temperature, you had a temperature drop of 15 degrees Celsius over a duration of 2 minutes. After the 2 minutes, now you have a temperature difference between the water and the ambient of how much? You have 60 degrees Celsius, which means the temperature difference is low, which means rate of heat loss or rate of heat flow will also be less, which means within the next 2 minutes, it is not going to lose 15 degrees Celsius. So let's say it loses maybe 13. So 82 minus 13 gives you 72 degrees Celsius. So after at the 4-minute mark, you're going to get maybe 72. So if you keep on plotting all of this value, I'm not going to write all these numbers because I am not very good mathematician in my head. So, but if you do plot all these values, and this is our ambient temperature, the temperature of this water, hot water, can never go below this level because it is being in contact with the atmosphere. So the water cannot be cooler than atmosphere. So in this cooling curve is going to look somewhat like this. It is going to become asymptote with the room temperature. Or at some point, for practical reasons, we can make it touch the 25 degrees Celsius mark for practical reasons. Because, well, we can say that it is now perfect at room temperature. The thermometer doesn't show us much to variation from 25 degrees Celsius. You can consider it to be 25 degrees Celsius. But in true sense, this is the key proportion that you need to understand. That when the higher the temperature difference between the hot and the cold object, the heat flow rate or power or rate of heat loss would be much higher. And as the temperature difference becomes smaller, the tendency to lose heat would become smaller and smaller and smaller and even smaller, which means the further cool it becomes, the less heat it loses, which means it subsequently experiences even less temperature drop. And that process keeps on happening. Keeps on happening. So that's why this graph looks like a decreasing gradient curve, because the rate of heat loss is not going to be constant. With lower temperature, the rate of heat loss is going to be less. এ পর্যন্ত বুঝা গেছে কিনা?
Yes, sir.
Everyone else? এ পর্যন্ত কোনো কোশ্চেন? No.
No,
Okay.
sir.
We're going to take a break. This is exactly 6.00, so we're going to resume class at around 6:10. Thank you. We resume the recording. So this is the preliminary idea that how does the temperature time curve for an object that is cooling under the effect of room temperature looks like. It is a decreasing gradient curve because the rate of heat flow is directly proportional to the temperature difference. One thing you should know that this proportionality is not in your syllabus. This is not in your syllabus. Not in your syllabus. However, this proportionality or this underlying principle is the reason why this curve looks like a decreasing gradient curve. This graph, however, is in your syllabus. The reason I started from this point and slowly went on to draw this curve and explain this whole experiment thing is to make sense to you, all of you, that how this curve is going to look like for a practical sense and why this looks like this so that you can understand it better. But this proportionality is not in your syllabus. For certain cases, if it does show up, it can be considered within the shaded boundary of the syllabus. So it's not within a defined boundary. But then again, if you are learning this curve, it is quite obvious. It may be quite obvious for within some examiner's mind that, well, kids are going to learn why the shape of this curve is like this. So they might as well ask, they should as well ask their teachers that why the curve is like this. So they're supposed to know this. So they might actually assume that this proportionality should be known to you. So I recommend that you learn this. This will be a part of the lecture anyway, because we just discussed and recorded the whole lecture. So you just know how this graph looks. Okay, getting back to the thermometer thing. The idea of the thermometer is that whenever we will, this is the basic shape of the thermometer. So we're going to need this thermometer shape information to discuss these three properties. So I'm going to discuss these three things as properties of thermometer. This is the term that we are going to use. And I'm going to also use another word, characteristics of thermometers. These two terms, properties of characteristics, are not within your syllabus. These are just some terms that I came up with to make it easier to make sense. Because sensitivity, range, and linearity are three different properties of the thermometer, or you can say aspect. There are multiple different physical property variation or physical changes, or visible and achievable geometric or shape-wise or length-wise or diameter-wise or material-wise changes that we can bring about within a thermometer to show us different changes that we can do to control these properties. So Those characteristics can be written over here. Actually, I'm going to find out the note that has this stuff so that I don't have to remember them from brain. I'm going to compile all of these stuff within a very good handwritten note, or maybe a typed one, and you're going to receive the email, receive this booklet within, let's say, a week. Currently, our printers are all busy with the mock things, so it's taking a while. And also, I haven't compiled the note yet, so that's also another reason. But you're going to have this all written down, so don't write anything for the time being. It's not necessary. If you have to write anything, I'll tell you that copy this or write this or whatever. Where is the O levels thermometer? Or is all the static? Just write thermo, not thermo. Thermo. So yeah, this one. Open file location. It is in this chapter. So let's have a look at this one. So I wrote these three properties in this sequence because I preferred it this way. And there is also a fourth property that we define as responsiveness. This is also a term that you have to understand. All this is not about syllabus, but questions do come from this property. So let's have a look at these definitions and let's try to make sense of this one. I'm gonna give all of this to you, so don't bother about that. কখন পাবো বা কিভাবে স্যার দিবেন কি না দিবেন না, definitely তোমাদেরকে দিব. You just have to hold your horses. Have a look. Linearity. What do we mean by linearity? Linearity means same amount of property change for equal amount of temperature change is linearity. It's basically a word description for that proportionality equation that we just saw in our last class, that the change of temperature is going to be directly proportional to the change of thermometric property. So this proportionality should be maintained over the entire working range of the thermometer. If this proportionality is not maintained, then we cannot use that thermometer for our purpose. So same amount of time. So have a look at the definition. Same amount of property change for equal amount of temperature change is linearity, which means no matter how high temperature you are operating at, or no matter how low temperature you are operating at, if that thermometer doesn't have linearity, then it would not be very useful to measure temperature. Equal amount of temperature change should be responsible for equal amount of property change and vice versa. Sensitivity, number two sensitivity says change in thermometric property per unit temperature change is full stop. So this is the phrase, not a full sentence over here. So what is sensitivity? Sensitivity is change in thermometric property per unit temperature change, which basically means delta X per degree Celsius. So for how much volume expansion happens for each degree Celsius of temperature increase, how much length increase happens for each degree of temperature increase, if degree Celsius of temperature increase, how much resistance changes, how much EMF is gained, how much color change happens, or how much pressure change happens for a fixed amount of gas. You can consider a lot of different thermometric properties which are relevant. How much does that happen for a given thermometer per unit temperature change? That's what we call sensitivity. So if a thermometer has more change of thermometric property for 1 degree Celsius, for example, if you consider two thermometers, so let me just draw two thermometers over here and give a bit of an idea for comparison. I'd like to copy this thermometer. Where is the thermometer? Thermometer show up. Okay, here you are. So let me try to copy this up. Oh, I cannot use mouse. So let me use somewhere over here maybe. Why is it so difficult to actually? For the next part, I might as well copy a picture from the MCQ paper. That's easier to deal with. See now the stem S চলে গেছে কোথায় জানো 100 এ 1 চলে গেছে আরেক জায়গায় Boom. Now we have the good figures that we are looking for. So if you try to find out a good thermometer picture, yeah, this is good. I like this one. Copy image. Let me get rid of all of this stuff. Good. And another one. Okay. So if we consider that we have two thermometers which are similar, if not exactly the same, let's say they have some of their characteristics difference, but the way they behave is that if we increase the temperature by equal amount of photo for both of them, let's say both of the thermometer were made to experience 5 degrees Celsius 5 degrees Celsius temperature increase. So delta theta is 5 degrees Celsius. Let's say the liquid column or the mercury column that rises for this thing in terms of length, not in terms of the gradation, in terms of length, let's say this mercury column increases by, let's say, 2 centimeter, and let's say this thermometer's mercury column increases by 2.5 centimeter. So let's say this is the scenario for these two thermometers, which are similar in construction but not exactly identical. So they have a bit of a difference in their length. So if this is happening, we'll say that this one is less sensitive and this one is more sensitive, because this one is showing us a much bigger amount of change for 1 degree Celsius for per degree Celsius temperature increase. এই কনসেপ্টটা বুঝা গেছে কিনা বলবান?
Yes, sir.
What do I have here? Oh, I don't know what this is. Okay, so that's the first thing. Sorry, second thing, sensitivity. If you could read further, more sensitive thermometer gains more fraction is এটা is হবে in the same temperature range, that is more precise readings. For example, a thermometer with 20 divisions between 0 to 5 degrees Celsius is more sensitive than one that has 10 divisions for the same temperature range. So if you think about, if you have two different thermometers, both of which have a measurable temperature range of 0 to 5 degrees Celsius, that's not the full range. Let's say they can measure a whole lot of different temperature, but if it so happens that for one thermometer, for 0 to 5 degrees Celsius temperature difference, you have 20 divisions. So in this case, each division is going to give you 5 by 20, 5 by 20, which is 0.04. Sorry, 0.4 degrees Celsius. That is going to be the value of each small division. Am I correct or am I not correct? 5 divided by 20 করলে কত হয়? 5 by 20. 0.25. Sorry, my bad. So in the case, each small division for this thermometer, which has 20 divisions over the range of 0 to 5 degrees Celsius, each gap or each small division is going to give you 0.25 degrees Celsius. So you can measure up to that much precision, one fraction or 1/4 of a degree Celsius. Whereas if another thermometer has only 10 divisions in it, each small division is going to give you 0.5 degrees Celsius. So you are simply going to lose the precision of the first one. So we say that the first one is more precise compared to the second one. You might wonder that, well, why can't all thermometers have a very large number of lines within them for the same temperature change? That is a question that has to be answered using some physical properties. Try to think about it. If you consider the construction of a thermometer, let's say this is a thermometer, okay? To make sense, let me just make it large. We're gonna have a look at it. What you need to understand that these are the lines, these black lines are the printed lines on the thermometer stem, which allows us to take a reading of this mercury level. To be able to see these lines have to have some thickness. By geometric definition, lines are not supposed to have thickness, but if you think for a realistic scenario, practical purposes, these lines have to have some thicknesses so that we can actually make them read or see the alignment of these lines with the level of the mercury, so that we can take a reading out of the thermometer. So because these lines do have some thickness, there is a practical reason, or there is a practical limit, precisely exactly how many lines can you put within a small amount of gap. I mean, if you come to think about it, let's say you are going to draw a line using a printing machine that is going to have a thickness of, let's say, 0.1 millimeter. So it's a pretty thin line. Now, sorry, 0.1 millimeter. So consider that the thickness of this line, printed line, is 0.1 millimeter. Now, if you have a space of, let's say, perfectly 5 millimeter for a certain temperature increase, which is actually half centimeter, how many lines can be actually put within this gap that so that you can actually distinguish these lines? You have to think that if you place these lines one upon another, stack by stack, touching each other, one up to another, touching each other, which is basically going to give you a whole black continuous pattern without any gap in between, so not going to be useful. The maximum number of lines, individual lines you can place over here is 5 divided by 0.01, gives you how much? 5 into 100, 500 lines. But drawing 500 lines over here practically diminishes the total usefulness of this thermometer, because you have a lot of lines, but you cannot take reading from any of these lines because none of these lines are individually distinguishable. Maybe if you don't want to give 500 lines, let's say if you want to put 200 of these lines, in that case, the gap between is going to be 5 divided by 200. So it's going to give you how much? How much is 5 by 200? 0.025. So in that case, your gap is going to be 0.025. আমি কি এটা ভুল লিখছি? হ্যাঁ, এখানে একটা 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 0.0 বেশি লিখে দিয়েছি। I'm such a dumb. Hold on, sorry, I made some mess. I'm gonna rub this off and actually redo the whole calculation. Okay, let's say one of these lines has a thickness of 0.1 millimeter. So if we have a space of 5 millimeter, the maximum number of lines we could possibly draw while touching each other like this, I mean without any gap in between, totally touching each other, can be 50 lines. If we don't want to draw 50 lines, let's say if we want to draw 20 lines, then how much should be the available gap? So 5 divided by 20 gives you 1 by 4, which is 0.25. So in that case, from one line to the next line, you're going to have 0.25 millimeter of gap. Now, try to understand what I'm trying to mean. To make sense, I'm going to draw a much thicker line. Let's say I'm going to use this one. Consider that this is highly magnified. Consider this is highly magnified. This is one of the line, and this is another of the line, and this is another of the line. These are the lines on the on the thermometer body. What you need to understand that the gap between the lines is gonna be 0.25 millimeter, whereas the individual thickness of these lines is 0.1 millimeter, which means if you measure from one end of this line to the other end of this line, this is 0.1 millimeter. You need this much thick of a line for it to be visible. And the gap between the lines, which means if I draw from center of this line, let me just zoom in a little bit so that it can actually make sense. So from the center of this line to the center of this line, this gap is going to be 0.25. Or I can say also, for the sake of easy understanding, from the edge of a line to the edge of this other line, starting edge of this other line, so a bit too much, edge of this other line, this much gap is supposed to be 0.25 millimeter. So practically speaking, how much gap is this? How much gap is this gonna be? Can someone tell me? A gap to কত হবে? The actual white space between the two lines. If you draw 20 lines in 5 millimeter, how much is that gonna be? White space is gonna be how big? Anyone? No one?
Sir, can you repeat again?
I'll repeat the question. Hear me out. I want all of you to understand this part because this is important to understand the concept of sensitivity, to make sense of it. Because here's the deal, kids. This part that I'm about to discuss about the sensitivity, range, linearity, and responsiveness can become quite confusing if you don't understand how it works. You cannot memorize this, I guarantee you. No matter how good of a note, no matter how precise, no matter how elaborate notes you have, you cannot memorize this and be successful about these MCQs or about the questions as well. You really have to understand this. That's why I'm trying to go deep and make sense with you with much detailed examples. So please try to understand. And if you have confusion, ask me. What I was talking about is that, let's say for a thermometer, we are going to mark these lines with a printing mechanism. And let's say we have used a pretty sharp printer where the individual thickness of these lines is going to be 0.1 millimeter. all of these lines, the width of these lines are going to be 0.1 millimeter. If we have a 5 millimeter gap within this space, and if we decide to divide this 5 millimeter space using 20 lines or using 20 gaps, the in-between gap between two lines is going to be 0.25 millimeter. In-between gap between two of these lines is going to be 0.25 millimeter. So this was represented over here like this. Let's say these are the lines which are going to use. This is highly magnified. So the thickness of this line, it means this much is 0.1 millimeter, the individual thickness of this line. Whereas the distance from the center of one line to the center of other line, or basically speaking that the distance between the two lines is going to be 0.25 millimeter. Or in other words, I can say distance from the top of the line to the top of the next line, I mean from edge to edge, or you can also say from bottom to bottom edge, that also works. I mean center to center, edge to edge, top to top or bottom to bottom is also the same thing. All of these measurements are going to be 0.25 millimeter. My question was, how much would be the in-between gap between these two lines over here? What would be this one? How much would be this one?
Sir, is it somehow 0.15?
It is exactly 0.15.
Okay.
বললাম বুঝতেছে কি বলছি? Everyone, do you understand what I'm saying? So if we want to grade this 5 millimeter space with 20 divisions, then with lines which are 0.1 millimeter thick, 0.1 millimeter means 1/10 of a millimeter. So it's actually a pretty thin line, but it's possible to achieve with available printing mechanisms. But in that case, drawing 20 lines would mean that the gap in between is going to be 0.15 millimeter. So we're going to have these lines really close to each other. I mean, pretty much like this. Now, here is the catch. This much close lines are good for high precision, because in this case, each of these division is going to be pretty good. Pretty good means, let's say within this 5 centimeter space, we had a total amount of temperature change of, let's say, 2 degrees Celsius. 2 degrees Celsius. So তুমি যদি 2 degrees Celsius কে তুমি যদি 20 division করো, you're going to get 0.1 degrees Celsius per division. This is actually really good, like super good. Hold on just a second, I have an unavoidable call coming up. Just a second. So which is in the recording. So these lines are going to be really close to each other. Now the question is that having these many lines, having 5 millimeter of physical gap represents a temperature difference of 2 degrees Celsius. And if we do draw 20 lines in between this 5 millimeter space, each of this gap is going to represent 0.1 degrees Celsius, which is, in terms of regular liquid in glass thermometer, is a pretty good precision. If you ask me, it's a really good precision. But the question that I want you to think about is that if we actually make these closed lines, where the gap between the lines is going to be 0.15 millimeters, how many people of the world are going to be able to use this thermometer for actual measurement? How many people have enough good eyesight to be able to decipher the gap, or be able to look at this gap precisely and be able to use this measurement for actual useful purposes? How many now? How many? Is this number going to be pretty big, or is this number going to be pretty small? Just I want to give me some opinion about that. How many people can? I mean, large number of people or less number of people? Few number of people. What do you think?
Few number of people.
Few number of people. So that actually diminishes the practical usefulness of a thermometer. I mean, this thermometer is going to be pretty useful in terms of its precision, but the utility of this thermometer is going to be pretty diminished. So this actually is the dilemma that we have to solve. Using modern technological advancement or modern manufacturing machines, we can actually draw a huge number of lines within a spacing. There are mechanical devices which can draw thousands of lines within 1 millimeter. These type of devices are called diffraction grating, which you're going to come to learn about in your AS level. So it's possible for us to manufacture these kind of devices, like drawing 1,000 lines within 1 millimeter space. It's not impossible. It's possible. We have that technology available to us as human beings within our grasp. We have that technology. But drawing this many lines is not going to be practical. This is actually the thing, that if we really want to increase the sensitivity of a thermometer, just drawing a lot of lines within a small amount of space is not a good idea. If you think that there is an alternative version that we can do, which we're going to talk about in measuring cylinder. Let's say other than drawing all of these 20 lines, one stacked upon another, how about if we tried this? Let me draw this right over here, and I cannot actually erase this thing. So let me just move this a little bit. How about if we did this? Let's say this is the thermometer body. Let me draw it black. Let's say this is the thermometer body, big thermometer body, because it's a highly magnified view. Actually, I should not draw that dome, because I'm trying to show you in between a location of the mercury. So let me just rub this off and maybe draw a break sign. Do you kids understand the meaning of the break sign? We talked about break sign in our earlier chapters.
Yes, sir.
It's a break part, or it's a continuous part of the whole thing. Let's say this is the stem that we have within the mercury column, where the mercury is going to rise. Sorry, not the stem, this is the board that we have. So also very magnified, and maybe not to scale, but disregard that. Let's say we still want, this thermometer still gives us, for a 5 degrees Celsius temperature change, this thermometer still gives us, sorry, for 5 degrees Celsius change, for 2 degrees Celsius temperature increase, let me specify that. For 2 degrees Celsius temperature increase, this thermometer gives us a 5 centimeter amount of height increase, and we still want to do 20 divisions within this space. So other than drawing these lines one on top of each other, there is an alternative version or alternative way we can do. You have to understand this whole thing is actually a glass cylinder. This is a side view of a glass cylinder. What we can do is we can draw a vertical line over here. And then draw these lines on either side. Let's say we're going to draw one of these lines over here. Let's say this is our 0 millimeter mark. Oh, forget about 0 millimeter. Let's say this is our first mark. And for in this fashion, we would draw this over here. But let's say now, to make it more usable, let's say we're going to draw the second line exactly 0.15 millimeter apart, but we're going to draw it on the left side. And then with another above another 0.15 millimeter, we're going to draw another line on the right side, and then on the left, and then on the right, and then on the left, and then on the right. We can also get it like this, right? Think about it. Is it possible to achieve?
Yes, sir.
It is very much possible to achieve. Now my question to you is that if this is the scenario, how much would be the gap of between from line to line over here? How much would be this much gap?
So you say 0.15 between each line, right?
For
On each
overstacked,
side?
for stacked
0.3.
So it's 0.3.
No, it's not 0.3. I'll show you why it is not 0.3. Let me just zoom on it, like even more zoom, because whiteboard allows it. Okay, fine. I cannot zoom it more. Okay, I'll try to draw this in a zoomed fashion over here. Let me choose a bit thicker line. Let's say this is this line. This is the midline over here. So let's say one line is drawn over here. The second line is drawn over here. The third line is drawn over here, and then this is this line, and this is this line. Think about it. What is the thickness? What is the thickness of one of this line? Remember? How much was it?
0.2.
0.1 millimeter. Beautiful. This is also 0.1 millimeter. And because these two things are representing two gaps, which means from one edge to another edge is how much?
0.
0 point double of this. Earlier this was 0.25. So now this should be how much? Double of that. So this much is how much? 0.5 millimeter, right? Now you can very easily tell me how much this should be.
0.4.
0.4 is the correct response. Yes. Do you understand the math here? তোমাদের এই ডিটেইলস লেভেলের ম্যাথ তোমাদের করা লাগবে না। I'm showing you these parts to give you a practical understanding how devices work, how calibration work, what is the magic of calibration that makes devices more useful or less useful, to give you that sense of calibration. So this is actually 0.4 millimeter. Now think about it. It's the same device, graded with the same number of lines, 20 lines within 5 centimeter, representing 2 degrees Celsius. But wouldn't this device be far too useful compared to if it was drawn like that? I mean, wouldn't this be more easily readable?
Yes.
Do all of you agree that taking reading out of this scale would be easier compared to taking a reading of this scale? এটা কি সবাই agree করতেছো কিনা দেখো?
Yes, sir.
Because the gaps are pretty far apart. So this actually brings us to the idea that for us to be able to concentrate on close parallel lines and be able to take reading out of that scale, those lines have to have some convenient gap in between. I'm using the term convenient. Those lines have to have some convenient gap between them. If you reduce that convenient gap, then the utility or the usefulness or the application for that device becomes limited in terms of number of people who can use it. So আমরা চাইলে, so even if we want, no matter how much we want, we cannot divide a certain amount of space in a very large number of divisions. There is a practical limit for how many lines can we actually draw within a certain space. This actually brings us to the idea for the limitation of sensitivity. If we really want to make a thermometer good sensitive, then we have to rather design a thermometer that will give us a much bigger length increase for the small temperature change. Let's say if we could design a thermometer, other than trying to achieve a high precision on this thermometer, let's say we design another thermometer which gives us, for 2 degrees Celsius, it gives us a length increase of, let's say, 20 centimeter. Let's say we design a thermometer like that for 2 degrees Celsius temperature change, it gives us a length change of mercury column or liquid column change of 20 centimeter. This would mean what? The amount of length the amount of mercury length change that will happen for only 2 degrees Celsius is massive, right? 20 centimeters is a pretty massive length for a thermometer. And you can grade this at a huge number of spacing. I mean, you can even if you mark this as at 1 millimeter spacing, because 1 millimeter is very easily visible. If you look at your small rulers, transparent rulers, you can see that observing 1 millimeter gap for our eye is quite convenient. We are good with that. 1 millimeter is a good spacing. So even if we divide this thing with 1 millimeter spacing, so let's say 20 centimeter divided by 0.1 centimeter, how many lines do you get? You get 200 lines, right? Or 200 divisions. I'm going to write 200 divisions. We can have 200 divisions for this scale, where each of these divisions are going to be 1 millimeter apart. So if we can make 200 divisions for 2 degrees Celsius, how much would each of these gap represent? 2 degrees Celsius divided by 200. So how much do you get? 0.01 degrees Celsius. Isn't this a far too superior sensitive thermometer compared to this one? Because over here, each gap was only giving us how much? 0. Have a look. If we had 20 divisions, where is the calculation? Here it is. If we divided 2 degrees Celsius in 20 divisions, we had 0.1 degrees Celsius. But if we could divide 2 degrees Celsius into 200 divisions, we're going to have 0.01 degrees Celsius. So this can give us smaller fraction of that temperature. So this is definitely more sensitive than this. এই পর্যন্ত বুঝা গেছে কিনা?
Yes, sir.
Any questions so far about this whole thing? I showed you a lot of drawing and a lot of calculation, but is the gist of the whole discussion understandable?
Yes, sir.
So what we can essentially understand from this discussion is that the only preferable way to have a more sensitive thermometer is to make the length increase of the liquid inside the bore more for a small temperature change. That is the more practical, pragmatic way. For a thermometer that should give us a small height change or small length change for a certain temperature, attempting to draw a lot of lines within that small gap to achieve a high sensitivity is not a very practical solution, because that will limit the usage of that thermometer. এই পর্যন্ত আমরা বুঝতে পারছি কিনা সবাই?
Yes, sir.
Okay. So let's look at the third definition over here. Range. Range is pretty simple. The difference between the maximum and the minimum temperature measurable by a thermometer is the range. Basic kotha hocche, if we have a thermometer, let's say we have a thermometer over here, you can have a look at the thermometer over here. This thermometer is plotted in Fahrenheit degrees Celsius. You don't have to deal with Fahrenheit in your syllabus, so disregard that. But still, this is labeled in Fahrenheit. If you just consider that this is okay, let's consider this Fahrenheit. So the range of this printed thermometer is the difference between this temperature and this temperature. Now, can someone tell me what is the difference of these two temperature in degree Fahrenheit? First, tell me, is this 20 all right?
It's -20.
It's supposed to be -20. Beautiful. And if you saw, what is the temperature represented by this very lowest line? What is the temperature value of this one?
-10.
Oh.
-30.
This is -10. This is -20. Further down should be -30. So the
yeah.
so the range of this temperature, the range of this thermometer is 120 minus -30 gives you 150 degree Fahrenheit. That's practically the range of this thermometer. The difference between the maximum measurable temperature and the minimum measurable temperature using a thermometer is its range. Now, range of a thermometer is a pretty pretty basic thing. You have to understand that if a thermometer is designed to be long, it is supposed to have more range. I mean, the longer the tube, the more gradations can you have. So you will have more range. So increasing length gives you more range, decreasing range can give you less range, and vice versa. However, range can be affected by other characteristics as well. For example, sensitivity and range are typically opposite properties. So we're going to talk about those after a while. But just because the length part is really understandable easily, that if the thermometer is simply long, it can have more temperature measurement capability. So it is going to have more range and vice versa. So that's very simple. And then the last property that we have, NB. Sensitivity and range are opposite properties. That is, factors which increase sensitivity. Here I use the term factors, and in your today's discussion, I mentioned them as characteristics. You can know them. I mean, these are physical বৈশিষ্ট্য. বৈশিষ্ট্যের ইংলিশ কি হবে? বললাম বৈশিষ্ট্যের ইংলিশ কি?
Characteristics.
Okay, characteristics. These are physical characteristics of the thermometer which control these properties. So we're going to see about them. Don't worry. Responsiveness. The fourth property that we have to understand is responsiveness. Responsiveness definition হচ্ছে how fast a thermometer can react with rapidly varying temperature. I'll explain what this means, but read this out once again. How fast a thermometer can respond to rapidly varying temperature. Now, what does this mean? It means essentially is that try to think of a physical scenario. Actually, let me just draw this over here so that you can visualize this better. Let me use a fresh space, 100%. So let's say this is a bucket filled up with hot water. So we are just told this is hot water, or we could take our hands close to this bucket, not touching it because we don't know how hot this is, and we can actually see that this is hot water. And we're given a thermometer, basic laboratory thermometer. Typical laboratory thermometers have a temperature measurement range of -10 to 110. Let me just show you. No. Okay, okay. Anyway, I could actually choose any of those. This is a typical laboratory thermometer, but you can see over here that this laboratory thermometer has a capability to measure from -20 degrees Celsius all the way up to, this is 90, 100, 110, 120. So up to 120 degrees Celsius. So this laboratory thermometer can deal with range of 140 degrees Celsius. So 20 degrees Celsius below zero and 20 degrees Celsius above the 100 degrees Celsius. This is the practical range. But different thermometers can have different properties. For example, if I go for another thermometer, this is also -20 to 110. But the typical thermometers that we have access to within our laboratories, they usually run from -10 to 110, not 20 and 120. Typical thermometers that we have access, I mean, actually I own for my laboratory, they are from -10 to 110. Anyway, we have a little bit of space, a little bit of temperature measuring capability below zero and above zero. because it has some practical purposes. I'm going to talk about those purposes later, not for the timing. What I wanted to understand. So let's say this is an alcohol thermometer. This is alcohol is actually pure alcohol is a colorless liquid. So a colorless liquid would not be visible within a glass equipment. So we actually add some coloring agent within the alcohol. We add it in. We add those coloring agent. We chose those coloring agent uh, with proper consideration, and also add certain amount within the alcohol, so that that property for alcohol to have uniform temperature, the linearity property of the alcohol is not destroyed. So because you have to understand, the pure alcohol gives us linear behavior, which is good. So if you add some impurities within them, because that color is not alcohol, so it's basically an impurity for in terms of alcohol. So if we add some color within that, there is possibility that that linear behavior for the thermometric property might be actually convoluted, or might be destroyed, or might be hampered. We don't do that. We choose the color, and we also add a certain amount, so that that property is still intact for the workable range of this thermometer. Workable range in this case is for this thermometer -20 to 120. So the idea that I'm trying to give you is that, let's say we do have a thermometer in room temperature. So let's say this is a thermometer. I'm just going to draw a rough shape of a thermometer. So this is the thermometer, and it's currently at room temperature. So let's say this is the temperature of this thermometer is 25 degrees Celsius. We're going to put this right into here. Let me just put it not like that. Let me just actually put it within that, maybe. So we're going to put it right over here. We're going to make sure that the entire bulb of the thermometer is under the water surface, and only the bore should be above. So this is how it's put. And now the thing, from the instant you put the thermometer within the hot liquid, you have to wait for a while, because try to think in very minute terms. The moment you put this thermometer within this thing, it will not give you an instant reading. That's not how liquid in glass thermometers work, because you do understand that the heat from the heat energy from the hot liquid or hot water has to penetrate through the glass wall of the bulb and enter into the mercury or the alcohol within this bulb. You might wonder, why can't they penetrate through here and enter into the stem? Well, the heat is going to try to reach through here, but this stem is actually quite thick. Recall the structure of the thermometer. Have a look. The stem part glass wall is really thick, so heat transfer to this amount of thick glass is almost negligible. But the glass wall of the bulb is actually designed to be quite thin, because our aim is to facilitate energy flow through this bulb glass wall. So heat energy is going to flow in from from this hot liquid into this mercury, and this is going to cause an expansion of this mercury, and then the mercury column is going to slowly rise through this tube and go above 25 degrees Celsius mark. This process of height increase will keep on happening till the temperature of this mercury also reaches the temperature of the liquid. Let's say the temperature of this liquid was, let's say, 85 degrees Celsius, which we didn't know. We want to measure, but I'm just telling you because I want to make sense with you. The temperature of this mercury inside this thing is going to start rising from 20 degrees Celsius. It's going to go up, 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 up. And eventually, when the temperature of this mercury and the temperature of this water, they are both equal, only then the temperature will give us a reading. Now, here's the deal. It is very much possible that because this is a hot liquid and there is atmosphere all around, this water is going to start losing heat. Let's say from the point to the for the increase of the thermometer, let's say to rise the temperature of the thermometer, let's say it's going to take 1 minute. If it so happens that within that 1 minute that this temperature drops by, let's say, 3 degrees, 82 degrees Celsius, what we're going to measure over here, what will be the final temperature represented by this thermometer? Is it going to give us 85 or is it going to give us 82?
82.
It's going to give us 82, because that's the final temperature at which the mercury is currently at. So the mercury is, so here's the deal. The water body temperature was at 85 degrees Celsius. Mercury body temperature was initially at 25 degrees Celsius. Whenever we put them in contact, this one is going to start rising by taking heat from the water. Also, this is losing heat to the atmosphere and also to the mercury, or also to the thermometer. So this one's temperature is dropping. This one's temperature rise is going to be really fast, because we have a very small amount of liquid to be heated. Consider the amount of liquid over here, consider the amount of liquid over here. So this is going to rise up pretty fast, but it is still going to take some time. And eventually, let's say whenever the equilibrium happens, this equilibrium is happening at 2 degrees Celsius according to my problem. So within this 1 minute amount of time, the temperature of the hot body got reduced by 3 degrees Celsius. So here's the deal. This thermometer gave us a reading 1 minute after we put it into the hot body. This 1 minute is sort of like a reaction time. Get this idea? Sort of like, we are not going to use this time as a as a definitive reaction time factor, but this 1 minute is sort of like a reaction time for the thermometer. And this thermometer, and because of that 1 minute time, we are not actually measuring the exact initial temperature, we're measuring something else. Well, obviously, if we had enough lagging over here and we covered this whole thing with appropriate set of heat insulation and evaporation stopping mechanisms, so just a second, then maybe this temperature can be still maintained to 800 degrees Celsius. But even so, this thermometer is still going to take 1 minute of time to give us this reading. The measurement of temperature will not be instantaneous. This is true for all thermometers, because to give us a steady reading, true reading of the hot body, the temperature of the thermometer itself has to reach to that temperature. Thermometer has to be heated up to the temperature, and only then there will be thermal equilibrium, and only then can we take the reading out of the thermometer. So for that temperature of the thermometer to rise from its original temperature to that high temperature value, it is always going to take some time. That required amount of time might be very small for certain type of thermometers. For example, thermocouple thermometers takes a very small time. That required time can be very large for some other thermometer. For example, in this case, for an alcohol thermometer, that required time was 1 minute, but it can vary. Depending upon this varying amount of time that they require to give us a temperature reading is what we define as responsiveness. The thermometers which can give us reading pretty fast, we call them more responsive. Thermometers which gives us reading pretty slowly, which call them less responsive. So the reason we are using this term that how fast a thermometer can react with rapidly varying temperature has a reason. Let me tell you that reason. Let's say you have an object that is continuously undergoing some change in temperature. So let me give a physical example. Try to understand. Mone koro, এটা একটা AC room. There is an air conditioned room over here, and there is a door. This is a classroom where we have some AC running, and the AC is set at 24 degrees Celsius, so it is now working. So the room is supposed to be at 24 degrees Celsius, but there is a door. Now what happens? Every once in a while, some student comes in and some student goes out. Whenever this door is opened, hot air from the outside, let's say the ambient temperature on a summer day in, let's say in Bangladesh, is let's say 30 degrees Celsius. So whenever the door is open, some hot air enters and some cold air goes out. So the temperature for the atmosphere that is close to this door is not essentially 24 degrees Celsius. It has to be somewhere in between. Do you understand this part?
Yes, sir.
Because we are having actual temperature in a hot fluid exchange, so the temperature of this part cannot be exactly 24 degrees Celsius because the door is keeping undergoing continuous open. Now, if you want to measure exactly how much temperature change happens while the door was kept open, I mean, it's a automatically closing door, but whenever a person opens the door, let's say for 1 second or 2 seconds and enters through the door actually allows a bit of air exchange. If you want to measure this precise amount of temperature change, and we use a mercury in glass thermometer right over here, the question that I'm asking you, should this thermometer be able to give us that in between increase and drop of this temperature? Should we be able to see that rise up and fall down using a glass thermometer? Is it going to be possible? What do you think?
No.
It is not going to be possible because this amount of air would not have enough heat energy to either extract out from the bulb or not enough energy to actually penetrate into the bulb. And the responsiveness of this thermometer is practically pretty low for this purpose. So you are not going to see the in-between variations that whenever the door is kept closed for, let's say 1 minute, the temperature actually drops because the AC is working. And whenever the door is kept open for, let's say 5 seconds, the temperature rises a little bit because the hot air is entering. So if you want to actually see those variations of temperature while the door is open and while the door is closed, you have to use a really sensitive thermometer, not sensitive, really responsive thermometer that can actually cope or that can actually match with the fast changing temperature. So based upon this idea, we have defined this definition like this, that responsiveness is defined as how fast a thermometer can react with rapidly varying temperature. It means that if a thermometer can actually handle rapidly varying temperature and give us appropriate reading, it is quite responsive. If it can't, it's not responsive. this is the definition that your syllabus gives us. So I made up this example to make sense with this definition. But in general terms, what you can think about is that thermometers which have a large reaction time are less responsive. Thermometers which have a small reaction time are more responsive. That actually can help you to understand this better. But don't ever write about this large reaction time or small reaction time in your exam. That's not an acceptable or recognized term in terms of thermometer. I'm just using this idea of reaction time because you guys know about reaction time, so it might be easier for you to grasp the idea and store it in your brain. Responsiveness idea ta bujha geche kina?
Yes,
Clearly.
sir.
Okay, Shaptosh, you raised your hand, you had a question. Please come with the question.
Sir, I was going to ask that whether we had any way of measuring that initial temperature, which in that case that you drew the diagram, it was 85 degrees Celsius.
Yes, we would have to choose to use a thermometer that has a really high responsiveness. For example, thermocouple thermometer, or for example, pyrothermometer. Pyrothermometers are those which actually, have you guys ever seen a pyrothermometer? Or
No, sir.
radiation
No.
thermometer? One of the radiation thermometers, actually.
Sir, but still, is that 100% accurate?
Well, well, if you ask me about 100% accurate, here's the deal, kid. No device is 100% accurate. Whatever measurement we do, every measurement comes with some error, and we say that error, we define that error or the limitation of that equipment as uncertainty. As uncertainty. For example, if you are using, here's the deal, if you are using a meter rule to measure some length, the smallest fraction you can measure is 1 millimeter, right? Smallest length that you can measure is 1 millimeter, which means no matter what length you measure, your recorded length should always be in full multiple of 1 millimeter. But essentially every object in the universe are not designed to be in full multiple of 1 millimeters, are they? There are objects which have fraction lengths of 1 millimeter, right?
Yes, sir.
So whenever we are using a meter rule, we have an error margin of plus minus 1 millimeter. Our measurement might be 1 millimeter more than what it's supposed to be. Our measurement can be 1 millimeter less than what it's supposed to be. But that's the range of error that we have to be okay with if we are willing to use a meter rule. This is the property of a measuring device that we call uncertainty. So the uncertainty of a meter rule is plus minus 1 millimeter. So even if you use very precise equipments, like super good equipments, you always have some uncertainty. Nothing can be measured with absolute uncertainty. Absolute values can be only obtained from math. Measurements will always come with uncertainties or always come with some error, because there is no such equipment that can give you absolute measurement. None. Does it make sense?
Yes, sir.
Does it make you feel sad?
No, sir.
Well, it should, because you should feel that, well, we cannot measure anything accurately. What's the whole point of measurement? Well, even if we can't measure it accurately, there is a certain level of uncertainty that we can work with. I mean, you can aim to get 100% in your A-levels exam, but let's say if you don't get 100%, but to get pretty close, that's not as bad. Or maybe you do score, let's say, less than 100. Let's say you score maybe 98 or 97, and by scaling, you get 100% marks. That's also pretty good. Scaling happens because of the uncertainty thing, that your performance in that exam that you appeared in O-levels was significantly better compared to the average performance of all the kids of that session around the globe in that variant. So what you got eventually got rewarded. So your 97% raw mark got increased to 100%. So that's the advantage of uncertainty. So it's not essentially as bad, but that's the thing that we have to be okay with. That's my point. Number example টা বুঝছো?
Yes, sir.
Okay. So these are the 4 different properties we just talked about. So now we're going to see that what are the characteristics of the thermometer that actually affects the properties of the thermometer. There are multiple different things over here, but before I get into this part, I'm going to first show you some basic geometry, and I want you to appreciate this first so that you don't feel confused. Kids, try to understand this thing. If you have a certain cylindrical volume of liquid that has a large cross-sectional area, and the same volume of liquid kept in a small cross-sectional area, is the length of this liquid is going to be equal to, less than, or more than this column?
More
It's gonna
than
be
This is definitely going to be more, right?
yes.
Okay, এই জিনিসটা মাথায় রাখবা। Second thing, let's say you have this amount of volume of liquid that will undergo 1 degree Celsius temperature increase. In another case, you have this amount of liquid which will also undergo 1 degree Celsius temperature increase. Which is going to take more heat?
The bigger one.
Obviously the bigger one. So if they are both supplied heat at the same rate, I mean the rate of heat entering into this amount of liquids is exactly same. If they are supplied heat by the same rate, which one is going to take more time to reach to the equilibrium point?
The bigger one.
The bigger one. সবাই কি বুঝতেছো, এগ্রি করতেছো? Even if you're responding, you should agree with this information.
yes.
Okay, না বুঝলে আমাকে কোশ্চেন করো। Okay, the other thing, if both of these liquids are increased by the same 1 degree Celsius temperature, the increase in volume, let's say after 1 degree Celsius, the delta V for this one and then the delta V for this one, I mean the amount of increase for volume, which one is going to expand more?
The smaller one.
Okay, I'll tell you again. I'll give an example. Let's say you have a cube of an object of this much. Let's say whenever you increase the temperature of this cube by 1 degree Celsius, it increases in volume by let's say 5 centimeter cube. If you have a cube of double the side length, so this is a cube of double the side length, and if you increase the temperature of this one by 1 degree Celsius as well, what would be the change of volume of this cube?
Is it 25?
Okay, before I tell you the answer, I want all of you to hear me out once again. This is a cube that gives us, for 1 degree Celsius temperature, it increases in volume by 1.5 centimeter. I didn't give you the original volume. Whatever the original volume, the delta V for 1 degree Celsius increase is 5 centimeter cube. Now try to think about it. If we consider another cube that has double the side length, within this double the side length, how many of these cubes are available?
2 along each side.
Have a look. I'll draw and you can count.
4.
You can count. Count. Don't forget the cubes which are not seen because they are on the behind side of the face. Don't forget them. How many cubes are here?
24.
No.
8.
8 is
6, 8.
Oh yeah.
8 happens to be a correct response. You should see it. 1, 2, 3, 4 on the front side and 1, 2, 3, 4 on the back side, right?
Yes, sir.
That's one thing. If you want to think it in another way, let's say this one had a side length of x, and this one has a side length of 2x. So the volume of this one is x cube. Volume of that one is 2x whole cube. Gives you how much? So how many of x cubes? 8.
8.
So you have 8 cubes over. So now I'm asking you the question again. If this one, if the temperature of this one's is increased by 1 degree Celsius and this one undergoes a volume increase of 5 centimeter cube, how much would be the volume change of this whole thing, which has double the side length, for 1 degree Celsius? Remember, there are 8 cubes over here. So what would be the total volume change of this one? Each of the cube will undergo 5 centimeter cube volume increase.
40.
So this one will
40.
undergo by 40 centimeter cube of volume increase. That's the correct response. Does it make sense in basic idea?
Yes, sir.
So now
Yes.
I'm asking you this question once again. If we increase the temperature of both of these two amount of thermometric liquid inside the bulb, which one has a smaller volume and this one has a larger volume, if we increase them both of them by 1 degree Celsius, the change in volume should be bigger for which one?
The bigger one.
The bigger one. Do we all agree on this?
Yes.
এখানে আমি তিনটা জিনিস দেখালাম, একটা হচ্ছে ইকুয়াল ভলিউম সিলিন্ড্রিক্যাল শেপের জন্য হলে যেই ভলিউমে যেই সিলিন্ড্রিক্যাল শেপের ডায়ামিটার কম বা এরিয়া কম তার লেন্থ বেশি হবে, এটা হচ্ছে একটা জিনিস। দুই নম্বর জিনিস হচ্ছে যে অল্প লিকুইডের হিট লাগবে কম ইকুইলিব্রিয়ামে যাওয়ার জন্য, বেশি লিকুইডের হিট লাগবে বেশি ইকুইলিব্রিয়ামে যাওয়ার জন্য। অ্যাজ এ রেজাল্ট ইফ দে আর বোথ সাপ্লাইড হিট এট দ্য সেম রেট, অল্প লিকুইডের টাইম লাগবে কম এবং বেশি লিকুইডের টাইম লাগবে বেশি। এটা দেখা যাচ্ছে হচ্ছে এই পার্টটুকুতে। অ্যান্ড দেন আই এক্সপ্লেইন that the amount of volume increase that we're going to get for the smaller amount of bulb liquid is going to be small, and the amount of volume increase for the larger amount of bulb, larger size bulb, is going to be more. এই কয়টা ইনফরমেশন মাথায় রাখো so that we can actually make sense of the next information. So আমরা এই পার্টটা এখন দেখি। নাম্বার 1, bore diameter। আচ্ছা পোলামান, তোমাদেরকে আমি এই পার্টটা একটু পড়তে দিই। আচ্ছা এই দুইটা পয়েন্ট একটু পড়ো সবাই, পড়ে আগে মেক সেন্স করার চেষ্টা করো, তারপর আমি বুঝাবো। I want you to read through this. Whenever we're going to consider the change, I'm going to ask you what do you understand after a while. Just give me a little bit of time to get to set the premise for these points. When we're going to consider these characteristics changes, we're going to consider, or we're going to try to visualize two thermometers side by side, which are identical in all of their aspects, all of their physical characteristics, size, length, material, board thickness, and everything. I mean, all of them are same except for the variable that we're discussing. For example, in this case, we are discussing bore diameter. So I want you to visualize two thermometers side by side. They're of equal length. They have the same material glass. They have the same bulb size. They have the same bulb wall thickness. They have the same amount of inside liquid, amount of volume of liquid within the bulb. Those two liquids are also exactly same. Both of them can be mercury, both of them can be alcohol, both of them can be XYZ liquid, but they're the same liquid. The only way they're different is one has a thicker bore, the other one has a thinner bore. I want you to visualize that. So only one variable at a time. That's how we're going to judge them for the upcoming all the sequence. For example, the second variable that we are discussing is bulb size. So I want you to visualize two thermometers side by side, exactly identical. Everything is same except one has a small bulb, the other one has a large bulb. Or you can consider the large bulb first, small bulb second, doesn't matter, but only variation is in their bulb size. And bulb size getting bigger or smaller essentially means in the bigger bulb there is more mercury in the bigger bulb and there is less mercury within the smaller bulb. Do I make sense?
Yes, sir.
This is one of the ground for standardized test, that if you want to find out the effect of only one variable at a time, you have to make everything same except for that variable, and then you can find out the exclusive effect of that variable. So the first one, what did you understand from this one? After you read through this paragraph, what did you understand? Someone respond. You can respond in the voice chat, you can write in the chat, but write in all chat so that everyone can see, so that we can take that information for everyone, and I'm going to help you. What did you understand?
So when the bore is thicker, the length change for every given temperature change is less.
Good.
And as the length is occupying more space per change in temperature, so we cannot accumulate a larger range in that very thermometer.
For the thin bore diameter, we cannot
Inner bore diameter, yeah.
Good. So what Saptoshi said makes sense, but she used the large bore diameter in the first part and then the thin bore diameter in the second part, which can be a bit more confusing for the examiners if you write in that fashion in your exam. So I would recommend that you stick to the same variability. But anyway, I'll try to help you understand. What it says that thicker bore gives less sensitivity and more range, and vice versa. That's the statement. Why? Because if we have one bore that is thicker, so larger diameter, and one bore that is thinner, so smaller diameter, and if we apply same amount of temperature change to both of them will have the same amount of volume increase for the bulb liquid. but the amount of height gained by the liquid in the bore would be less for the large diameter, and the amount of height gained by the small diameter would be more, which means this will have more length, this one will have less length. So obviously this one will have more sensitivity, this one will have less sensitivity. And of course, because this is covering a larger length, so because both the thermometers are considered to be of exactly equal lengths, this one will reach to the top of the bore for earlier, and this one will take a much higher temperature to reach to the top of the bore, which means effectively this one will have a much smaller range. It will be done with this length. It will be this thermometer will fill up its length for a smaller temperature compared to the maximum temperature measurable by this one. So this one has a high sensitivity and less range. This one on the other hand has a smaller sensitivity but higher range. বুঝাচ্ছে?
Ji, sir.
Everyone else, কোনো question? If you
No,
did
sir.
understand this, please write yes in the say yes or write yes in the
Yes,
chat.
sir.
There are 12 people, so except for me there are 11 students. I had 3 responses so far, 4. Nuhan, Nuha.
Yes, sir.
Okay, I believe I got everyone. So this is the first variable. The second variable that we have, bulb size. Let's have a look. The bulb size says larger bulb contains more liquid, and so for the same temperature rise, it also expands more, which we just discussed within this variable. So for the same temperature change, this one expands more, this one expands less, which means this one will have a more sensitivity because this one will essentially give bigger height rise to the same bore. You have to understand that we are trying to consider in this case 2 thermometers, one of which has a big bulb, another has a small bulb, big on the right, small on the left, but they have the same bore diameter, same material, same thickness, same bulb wall thickness. Everything is same except for the size of the bulb. That's the only variable that we're dealing with. So in that scenario, so it expands more, hence it rises more in the bore, so it has more sensitivity, and since more liquid requires more heat to be in equilibrium with the object, it takes more time, so it has less responsiveness. So larger bulb size increases sensitivity, decreases range, and decreases responsiveness, and of course vice versa. বুঝা গেছে কিনা?
Yes, sir.
Okay, the next point we have is bulb wall thickness. Bulb wall thickness is basically how much thick that bulb wall is, which you can have a look for right over here. In this is we're talking about this much part. So if we have 2 thermometers which are identical in all aspects, that only one thermometer has a thin bulb wall, the other one has a thicker bulb wall. You have to understand that if this wall is thin, then the heat transfer can happen pretty fast because the heat has to travel through a much less poor conductor of material. Glass is a poor conductor of heat. So if the bulb wall is thin, then heat can flow in pretty fast. So you have a higher rate of heat exchange, which means your responsiveness will become high. The one that has a thin bulb wall allows for a higher rate of heat exchange, so your responsiveness will be high. It will take less time to give us the final temperature reading, and vice versa. So bulb wall thickness is a variable that only affects responsiveness, not the sensitivity, not the range, because those are not affected. It just affects the time. So it says the thicker bulb wall, much slower is the heat transfer process through it because glass is a bad conductor of heat. You could write poor. So thicker bulb gives less responsiveness and vice versa. Number 4, liquid with more heat capacity. No, the thing is, we didn't yet read the term heat capacity. So I'm going to keep this variable right here and not go into the discussion of this one. I'm going to pick up this property later whenever we have discussed the heat capacity, which is the next chapter. So for the time being, I'm holding off the explanation of number 4. I'm going to come back to this when we're going to discuss, when we'll be done discussing heat capacity in the next chapter. Number 5 is optional, liquid with more expansivity. More expansivity basically means the word itself is self-explanatory. It means that there are certain liquids which expand more compared to other liquids for the same temperature rise, for the same volume. For example, if you consider between mercury and alcohol is more expansive compared to mercury. It just is. It's a inherent property of that liquids. So if you use a more expansive liquid, you're going to have a higher sensitivity because it will rise through the bore much higher. And if you have less expansivity, you will have a less sensitivity. And cases where you have more sensitivity, you have less range, and vice versa. So that's what it says. More expansivity liquid may expand more for the same temperature change. So sensitivity increases and range decreases and vice versa. এখানে একটা প্রপার্টি লেখা হয় নাই, বলতো কোন প্রপার্টিটা লেখা হয় নাই, যে প্রপার্টি আমি একদম শুরুতে আলাপ করছিলাম। Does anyone remember which property is not discussed over here? I talked about this property when I was in this figure.
The entire size of the thermometer or this term?
I'd say length.
Oh yeah, the length.
Size is a sort of vague word because size could mean a lot of stuff. It could mean length, weight, breadth, inside diameter, outside diameter, volume. I mean, size is not a appreciated term in physics. You have to specify the measurable quantity. So the length of the thermometer is also a variable. Which property does the length affect?
Range.
And anything else?
Sensitivity.
No. Length does not affect sensitivity. If you have a longer length, you can accommodate more higher temperature. That's it. If everything else is same between two thermometer, one is shorter and another is longer, so you have the same bulb size, same bulb wall thickness, same bore diameter as well. So the amount of temperature, amount of height rise of the temperature of thermometric liquid within that bore for the same temperature value is essentially same. One simply can reach up to the highest level earlier, which has a smaller length, and the other one can reach up even higher because it has more space to go for. But the amount of increased per degree Celsius temperature is essentially same, right? Do you understand
Yes.
my point?
Yes, sir.
So that's why they would have the same sensitivity, but exclusively the one that is longer will have more range, obviously, for geometric purposes, properties, and vice versa. So length was not mentioned over here, but whenever you will have this note, I'm going to try to add 6-point length, and I'm going to write use your brain because I want to use your brain. So that's it. That's pretty much it for today's class. In our next class, hopefully we'll start the thermocol thermometer discussion, unless you ask me some problem from the density pressure. And once again, I forgot to discuss the timing shift for the Friday class because I really wanted to discuss this up to this point in today's class, which we could achieve. I'm pretty happy about it. I'm looking forward to have, yes, Saptarshi, you raise your hand.
Sir, you say that whenever we are changing, for example, when we are increasing the sensitivity, the range is decreasing automatically. So which is more preferable by the consumers, like a more sensitive thermometer or a thermometer with more range?
This is a very, very nice question. I'll answer this question in detail, but pretty fast because we're pretty much over time. What kind of thermometer is preferable for a certain user is exclusively dependent on what purpose that thermometer is going to be used for. Let's say you are working for this example. Let's say, where is that whiteboard? Let's say you are actually performing some experiment using this example. So if you want to do some actual experiment for this kind of measurement, what do you need? Do you actually need a huge range?
No.
You don't need a huge range, but you do appreciate a high sensitivity because the amount of temperature range that will be relevant for this case is not going to be more than 2-3 degrees. But if you can have much fractions, a lot of fractions within that 2-3 degrees, you can get more accurate data. And because, and I mean, for this purpose, you're going to need a thermometer that has a really high sensitivity, and also really high responsiveness, but a very small range you can work with, right?
Yes, sir.
And then again, if you try to think about some other industrial purpose, for example, let's say you are operating a blast furnace where you produce molten iron. You produce iron from ore, you extract iron, and you want to quality control that iron. In iron manufacturing, temperature is a very important factor. That what is the maximum temperature that iron alloy was pulled up to, and then it was allowed to cool down, and how did the cooling effect happen Is it a fast cooling or slow cooling? There can be a lot of variables, but the maximum temperature that you take the mixture alloy to is a very important factor. So if you work in a factory of that sort, you are gonna need you're gonna need a thermometer that should have really high temperature range, because you're gonna start your overheating from, let's say, what, room temperature, and then the temperature is going to start rising all the way up to, let's say, 500, 600, 652, 650, or 753 degrees Celsius. You have to have a good capability to read off that temperature precisely. So you are going to need a high sensitivity and high range at the same time. But responsiveness in this case might not be very important, because you're going to put the thermometer inside a blast furnace where heat is always available, and there is enough heat to heat up your thermometer within an instant. The amount of heat transfer rate is not a very important factor inside a blast furnace, inside a iron making furnace. So for that purpose, you are going to appreciate high sensitivity and high range at the same time, but the responsiveness, you can disregard that one. Do you get my point?
Yes, sir, I get it.
So it's totally dependent on the purpose that you're going to use it for. There is no hard and fast rule or rule of thumb that, well, this kind of thermometer is better than the other. It is all dependent on the use. Clear?
Yes, sir.
Beautiful.
Sir, I have another small confusion. Can I ask it?
Yeah, sure.
Small. So when we are changing the range sensitivity, the range is changing. So is it also mandatory that when we are changing the range, the sensitivity will also change?
Well,
Like
here's the deal. We do not we do not essentially change sensitivity or range by virtue by their own virtue. Sensitivity, range, and linearity, these are the properties which are affected by those characteristics. We change the characteristics, and that automatically changes one or two or three, all three of them. I mean, you cannot only say, hey, say that this thermometer is going to be made into more sensitive. You're not going to do that. You're going to change one of these things to change the sensitivity. Do you get my point?
Yes, sir.
Sensitivity is the outcome of these things. So you have to understand in that term. But the way it works, that for changes of characteristics that cause sensitivity increase will automatically cause a subsequent decrease of range, and vice versa. So it's not that increasing sensitivity will decrease range. That is actually true, but it would be better said that changes that cause sensitivity increase will obviously cause decreased range. That would be a better way to say that. Because sensitivity is a factor that is not automatically changed. It is changed by achieving something else. Make sense?
Yes, I get it. Yeah.
Beautiful. So kids, thank you very much for the additional 9 minutes. Goodbye. Allah Hafiz. Assalamu alaikum.